Sneaky Structures. So this will be the last problem of the sort where we show you a proof, and then we ask you to find any flaws within that proof. But before we get to the proof, we're going to need to go over some definitions. Suppose you're in a recitation, where every student in that recitation knows at least one other student in the recitation. Then we want to define a notion of connectedness for those students. We're going to say that two students are connected if there's some chain of students starting from the first student and ending at the second student, such that in each pair along that chain, the two students know each other. So for example, if Xavier knows Yvonne, and Yvonne knows Zachary, even if Xavier and Zachary don't directly know each other, because we can draw that chain between the three of them, we will say that Xavier and Zachary are connected. Now we're going to evaluate the claim that in such a recitation, where again, everyone knows at least one other person in the recitation, then every student is necessarily connected to every other student. Now would be a good time to pause the video and think to yourself, do I believe that? We've proposed a proof of this via induction on n, the number of students. As a base case, suppose that n is equal to 2. Then, by our definition, the first student in the recitation must necessarily know the second student in the recitation, because that's the only other student there is to know. Similarly, the second student must know the first student, and therefore they're connected. As our induction hypothesis now, suppose that for some k greater than or equal to 2, our claim holds for all groups of k students. Then as our induction step, consider a group of k plus 1 students. We can treat this group of k plus 1 students as sort of like a group of k students combined with some k plus first student. Well, by our induction hypothesis, we know that the group of k students must be fully connected. Every student in there is connected to every other student. Now for this k plus first student, they necessarily know at least one of the other students in the recitation by our definition. If they know any of those students, because that student must be connected to all the others, then they must also be connected, and thus the whole recitation will be connected. Now would be a good time to spend a little bit thinking about this proof, pause the video perhaps, and see, can you spot any flaws initially before we move on? Well, when I'm spotting flaws, the first place I'm going to turn is an example. So if we're walking through essentially the logic of this proof, we take a group of 3 like this, for example, and we're going to group it into the 2 students, our group of k, and our k plus first person. We see that Zachary is connected into this initial group of 2, so that's okay. And then if we take Zachary out of the picture, by our induction hypothesis, we have that these two are connected. Everything's holding pretty well so far. But what if we flipped this? What if we said that Yvonne was actually the k plus first person? And then the group of 2 was Xavier and Zachary. Well, Yvonne is connected into that group, but if we take Yvonne out, we don't actually see a connected group of 2 students. Something fishy seems to be going on with our induction hypothesis. And so maybe this indicates we might have a problem. Specifically, we can see such a problem in a counterexample like this. Here we have a recitation with 4 students, and each student clearly knows one other. Julia knows Xavier, Yvonne knows Zachary, but the whole group is not connected. There's no way to draw a path from Julia all the way to Zachary. So let's see if we can find this flaw we've spotted within the text of the proof itself. I'll give you a little bit of time to see if you can work out, first, what do you think this problem might be embedded in? So, one thing that jumps out to me initially about this proof is that it hides a lot of content in the phrase, "this works," in the induction hypothesis. So let's expand that a little bit first. This works here essentially just means that the claim holds, that every student knows at least one other, implies that for that recitation, all students are connected. So Now that we have this more specific definition, let's see how we can apply this later on. Well, in our induction step, we go to the usual, we've got the k+1 students, we treat it as a k-student recitation that we want to apply the induction hypothesis on, and a k+1 student. For the k+1 student, all we need to know is that they're connected to somebody in that k-student recitation. And that's okay, because we know they're connected to somebody else, and necessarily it has to be one of the other k-students. However, with the remaining k-students in the recitation, it gets a little bit trickier. We know by assumption that each of them is connected to at least one other student. But we don't know that that other student is within the k-students. It could be that k+1 student. And therefore, we cannot actually apply the induction hypothesis on that group of k. We do not have a group in which every student knows at least one other. This means the proof essentially falls apart. We don't know that those k-students are connected, and so we don't know that the last student being connected to one of them means that he or she is connected to all of the remainder either. Therefore, we're done. And really, this just emphasizes how careful we have to be in our wording. If there's one major takeaway here, it's to be precise, to write everything out, and to know exactly what you're applying in a case like this, not just to move forward with vague statements such as "this works."